Okay. Making myself bigger here. A little bit me right in the corner here to view. There's gonna be a lot of editing that has happened apparently. Okay. Okay, there we go. Let's hope it's recording. Okay. We shall see.
I hope so.
Okay, so today's nutrition, we're going to we're not going to have our traditional bones, muscles, and joint actions with this one. This one has a lot of information, so we're just going to go straight into the lecture here. We'll probably spend 2 days doing this lecture, because if we do it all at once, it's really dense. Did you bring a workbook today by chance?
No, but I have notes from other things.
No worries.
Right.
No worries. We'll do. I have it on me here, and then we can also just do some fictional ones as far as the calculations. Okay. We may even wait till calculations next week, but I at least want to get one case study out of the way. That way you can kind of figure out a workflow here. But most of today will be mostly going over the kind of the little bitty parts that add up to all the nutrition stuff we're going to do, all the little bitty things that are kind of the underlying concepts behind why these things work as far as calories in, calories out. So as far as macronutrients include dietary items that are needed greater in quantity than 1 gram per day to sustain life long term. That's going to be the macronutrients. So macro, large, big. Then we also have micronutrients. Micronutrients are going to be things that need less than 1 gram per day. Those are going to be more your vitamins and minerals and so forth. Macronutrients themselves are considered also energy yielding, meaning that once they are broken down to a usable form, they can produce energy for the body. In this instance, it's called ATP, adenosine triphosphate. As far as your macronutrients go, you're looking at carbohydrates, proteins, and lipids, or fats in other words. Technically, water can be considered a macronutrient. However, it does not directly yield energy, so we don't necessarily call it a true macronutrient. Though it is involved in pretty much every metabolic process in the body, it is not necessarily going to be macronutrient, energy yielding. Calories themselves are actually a scientific measure of heat. How they basically assign calorie values, they will actually put something in the container. Essentially, they'll burn it, and basically the amount of heat that it puts off from being combusted is how it will assign calories. Nowadays, we pretty much know what types of foods yield what type of calories, so I doubt they do that very much anymore as far as having to assign calorie values, but when we were just figuring out calories and how they worked, I'm sure it was done a lot more. Calories themselves are different measures of units. So you have calories with a little c, which is, say for instance, like you were doing the metric system, you have meters and millimeters, kind of the same difference in a sense. Calories are a smaller unit. Big C calories or kilocalories are larger units, and that's what we actually use as kilocalories when we look at food labels, which are 1,000 small C calories. Carbohydrates. So one of the important things for the carbohydrates is they have 4 kilocalories per gram. Or kcal. That would be a good abbreviation. As we talked about when we were talking about blood sugar regulation, the pancreas, glucagon, insulin, all that fun stuff, even our discussion question that we had. Going to be used to maintain blood sugar, spare its protein. A lot easier to just tap into stored carbohydrate stores than it is to strip skeletal muscle off to create energy. Also going to provide fiber, so a lot of our more whole grains and our vegetables are going to have fiber in them. So it's going to help us purge things from the body that are toxic, and then also help us form stools and all that fun stuff. For the most part, carbohydrates are going to be in two categories. We call them complex or simple carbs. Complex are going to be like your whole grains, your vegetables, things of that nature. Some of the vegetables can still be simple carbohydrate, kind of depends on where they fall in the glycemic index and other things. But essentially what happens is you have chains of carbohydrates, and if you have one or two carbohydrate chains that make up the molecule, then it's a simple. If you have more than two, then it's going to become a complex carbohydrate. And we'll talk about those classifications a little bit later here. For the most part, carbs are not a bad thing. Too many simple carbs, even too many complex carbs can cause issues in multiple aspects. Obesity, type 2 diabetes, can affect type 1 diabetes if you're not controlling insulin blood sugar levels as well. But type 1 diabetes is nothing that you've done to yourself. That's a genetic thing that happens. So just a condition. Type 2 diabetes is the one that you produce yourself by misusing carbs for the most part. Carbohydrates themselves are the preferred energy source for the central nervous system. They can be stored as glycogen in the skeletal muscle and also the liver. We already discussed this in the last chapter, but glucagon is the hormone that comes from the pancreas that helps release glycogen stores from the muscle and liver, which are the stored carbohydrates. About 300 grams altogether between the two. Also going to be the primary fuel source for intense activity lasting more than 90 seconds. And we'll get into those energy systems. I know personally in this campus, we've talked about energy systems just a little bit in the red section, but we will get there formally. This is a slide talking a little more about the complex and simple carbohydrates here. The technical names can be polysaccharides, disaccharides, and monosaccharides. Poly meaning many, going to have more molecules, harder to tear apart, takes a little bit longer time. So you have a little bit less sharp insulin spike when the blood sugar starts to arise. With those, we usually have our fiber being polysaccharides, starches that come from plants, and glycogen, which is stored carbohydrates that you would eat from like animal protein that comes from the muscle you eat from the animals. It's kind of a nasty thought. I would always like to just think the grocery stores just create meat. I don't like to think about the process that really goes into it. Which is funny because I hunt, but I still like detach myself from meat being animal. As far as simple carbohydrates, we have the terms disaccharide and monosaccharide. Di meaning two, mono meaning one, and those are going to be our simple carbohydrates, things like fructose, glucose, lactose, sucrose, and all the other ones there, basically either disaccharides or monosaccharides. They can be found in various things. So if you see those on food labels, we know that automatically they're going to be disaccharides, monosaccharides, essentially simple carbohydrates. Carbohydrate sources. So what this slide's kind of top by is going to be nutrient density. So nutrient density describes what other benefits we're getting other than just the calories, essentially. So you have your at water values for for carbohydrates. So that basically means what the food label says is the at-water value. Why it's called the at-water value, I will need to look that up one day. I've gone through the slides numerous times. I'm not exactly sure what that necessarily means, but we do know that the at-water value is 4 calories per gram, what they assign on the food labels. But actually, the nutrient density of the food is going to vary quite a bit. Not only the complexity of the carbohydrate, but also what other things you're getting. So if we have this disaccharide here, and let's say this disaccharide is from a donut. After processing all these fun things, maybe you have a few vitamins that still linger on from the grain that was used. Maybe you still have some things that, despite all the processing, have survived. And you're still getting a little bit more than just these base calories. So say this is a gram. You get 4 kcals from this, you're getting maybe a little bit of vitamin A there, a little vitamin C. In no way is that actually indicative of what you get from donuts. I'm just purely for example. And then you have another disaccharide. This is donut. You have another disaccharide over here, and this guy is going to be carrot. Shouldn't be processed. If you have a fried or glazed carrot, then probably so. But we're going to just say this is like a raw carrot. Minerals. All this fun phytonutrient stuff. So as far as the calorie content goes, you're still getting 4 kcals from each. But however, when we look at what we're actually getting for those 4 kcals, over here we're getting dismal amounts of additional benefit, where over here we're getting tons of different minerals and vitamins and things that we're not going to have to now supplement with instead of actually just consuming them. So this is what they mean when they talk about empty calories. Empty calories doesn't mean they don't count or they're hollow or anything weird. It just literally means that you're not getting the full nutritional benefit because the food has been processed or nutrients have been taken away through the processing of the food. Does that kind of make sense?
Yeah.
Okay.
I like the diagrams.
Yeah. But essentially, it's the same nutrient value as far as calories go. So when it comes to weight loss, they're equal. When it comes to weight gain, they're equal. When it comes to the performance in between, they're not equal. Does that make sense? So we're trying to produce energy and all those things that have to accent our metabolism, not necessarily directly, but they help us produce hormones and help the metabolic process happen easier. Then your carrot's going to be much more superior.
So as long as you're in a deficit, you could be eating donuts all day long, still
could.
sleep. Your body's gonna look super different if you're doing that.
Yeah, you probably have type 2 diabetes eventually. Yeah, but essentially, you could. I mean, you could lose weight drinking beer. I feel like for a few weeks during the quarantine, I might have started a beer diet unintentionally. But essentially, you can lose weight eating anything, but how you're going to feel as far as performance goes and in between, just mentally and everything is there's differences. But as far as calories in, calories out, they're essentially the same in a sense. Got the gist of it? I can erase.
Yeah.
Okay. Okay. Yeah. So as far as intake, we're looking at 45 to 65% of total daily diet. It consists of carbohydrates, or in other words, 6 to 10 grams per kilogram of body weight. And that's a NASA recommendation. We have our own specific way of getting to some numbers. However, again, you're taking the NASA test, so you're not taking the FTA test, even though you do have a final project. But which you do need to use our method during the final project. But when it comes to the NASM test, you will need to know these numbers, not for calculations, because as far as the test goes, you don't need to know anything that you can't do on two hands, basically. But if they ask what percentage would be most appropriate, blah, 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 then you have to know these numbers. So 45 to 65% coming from carbohydrates, or in other words, 6 to 10 grams per kilogram of body weight, coming directly from your NASM textbook. The recommendation, why there's a range there. The range varies based on activity level, and specifically intense exercise as well. So if someone is doing a high manual labor job, then they need more carbohydrates. Or if they're doing high activity, like they're a professional athlete or doing training for an Ironman or whatever, then they're going to need more carbohydrates. It would be further to the right-hand, larger side of that scale. If they're sedentary in the office all day, then they're going to be the left hand of that scale. And it doesn't have to be static either. I know I've chatted with some people about the discussion question about alternating percentages from different campuses as far as getting less carbohydrates on days that you know you're going to be sedentary, or if you're going to have a highly active day with heavy exercise, like leg days, for instance, getting more carbohydrates in on that day, because you're going to be depleting your glycogen stores and that sort of thing. Have a lot less of a chance of actually storing fat if you're utilizing a high intensity exercise program or activity that day. Glycemic index, which I slightly remember that I referenced before. Glycemic index is going to talk about the sugariness of food, essentially. You also have glycemic load, which is a little bit different, but specifically we're talking about a glycemic index here. This can be scored on things as far as being complex or simple. Anything that's going to be high, have a high glycemic index and be above 70. Moderate will be a range between about 56 to 69, and low will be anything below 55 as far as a scoring basis. And you should have a chart in your book as well, as you can also Google these things. And a lot of the weight loss apps that you use to track will also have glycemic index charts or values assigned. Okay, protein. Protein is going to have the same caloric value as our carbohydrates, 4K calories per gram. Depending on the type of meat, these will vary, but the Atwater values, the assigned caloric value that you're going to see on labels is always going to be a standard 4 calories per gram. That's known for its role in muscle growth and repair, also has vital roles in development, maintenance, and repair of all tissues in the body. Also helps regulate fluid balance in the body, blood clotting, enzyme production, acid base, balance, immune functions, hormone production, and is a carrier for several nutrients. So we have a lot of things going on there. Protein itself is made up of carbon, hydrogen, oxygen, and nitrogen. Nitrogen being the one that causes the stinky pee if you have too much. If you've ever gone down to a Gold's bathroom in the morning and been unfortunate enough to catch some big bodybuilders in the stalls, you definitely can tell when someone's having too much. So that might have been a little too much information. Made up of a combination of amino acids, building blocks of protein. The body can synthesize all but 8 of the total 20 amino acids that make up protein. So of the 20, that basically makes all the amino acids that we're going to talk about. But 8 of them have to be eaten. So the body can use different things to combine to make these amino acids, except for 8 of these guys. Non-essential are going to be the ones that the bodies can produce. So if you see non-essential amino acid, that's going to be ones that we can basically produce ourselves without having to consume it. Essential amino acids, the ones that we have to consume. Then we have conditional or semi-essential, meaning that the body genetically may not be able to produce enough. There may be a condition that you have. It also may be age-wise infants. I think it's histidine. It's one with the H, and we'll see it here in a second. But there's some of them that the body cannot produce until a certain age, a few months after birth. I believe it has to do with breast milk. So here we got our list here. I'm not going to go through all these and pronounce them because you'll quickly learn that these are really, I guess they're not super hard to pronounce for most people, maybe just for me. We got our essentials there. We got isoleucine, leucine, lysine, methionine, phenylalanine, threonine, troponin, valine, being our essential amino acids. We move over to our semi, which I was talking about earlier. We got arginine and histidine. Hey, I got it right. Which are going to be semi-essential. Arginine, a lot of times people won't produce enough, so they need to supplement, especially if they're genetically predisposed. Histidine, I believe, is the one that isn't produced until shortly after birth. I believe at birth you cannot produce histidine, so you get it from breast milk, I believe. Okay, so words. Complete protein means that you're providing the meal that you're eating is providing all those 8 essential amino acids. Incomplete will be the ones that don't have all 8 essential amino acids, at least missing one, if not more. Typically, complete proteins are going to come from animal sources. And stereotypically, incomplete ones are going to come from plant sources. We also have what we call complementary proteins. Have you ever watched Survivor?
Mm-hmm.
What is the one thing they give them every challenge up front as far as food goes?
Every challenge?
Every challenge. I assume so. I haven't watched it in many years, but at least the earlier ones, I know they gave them a certain staple food to begin with.
I don't remember.
Beans and rice.
Beans and rice?
Beans and rice.
Okay.
Beans and rice are complementary protein, meaning that rice is actually deficient in one amino acid, and beans are deficient in one amino acid, so they're not complete, but together they make a complete. Because the other one is high in the other thing, the other one is high in the other thing that is lacking in each other's amino acid profile, so they actually create a complete. And that's how smart vegans and smart vegetarians go about making a complete amino acid profile for their diet, is to compare those things and make sure that they're meshing and making a complete protein. Not everybody really thinks about that when they get started. Sometimes they just jump head first, but gotta think about those things to a certain extent. As far as recommended intake, 10 to 35% of total calories throughout the day, according to NASM. And then as far as specific recommendations per kilogram of body weight, we're looking at 0.8 grams per kilogram of body weight for sedentary people. For athletes, it's going to increase to 1.2 to 1.7 grams per kilogram of body weight. And then for endurance athletes, we're looking at 1.2 to 1.4 grams per kilogram of body weight. And these are all NASM recommendations, so definitely remember these for the exam. We'll have a little bit different methodology when we get into the FDA-specific methodology, but these are the NASM ones. Specifically for my one student here. And then also for everybody listening to this, if you look at the bottom left of the screen, or my left, I think it's your left too when you're looking at it, I don't know. But you'll see the little NASM logo in the corner. That means that there's a good chance it's going to be on the exam. It's for sure on the study guide. And if it's on the study guide that's in the back of your course guide, then it means that it's definitely going to be a pool of questions on the exam. Yeah. So now lipids, or fats in other words. So as far as fats go, they're going to be the most calorie-dense nutrients that we have. 9 kcals per gram. So just over double what either carbs or protein will basically produce. So a few different fat substrates that are in the body. We have triglycerides, we have fatty acids, we have glycerol, phospholipids, and sterols. As far as triglycerides goes, a chemical or substrate in which most fats exist in food, such as meat, butter, and nuts, as well as in human fat cells. Fatty acids are a chain of carbons linked together, form the building blocks. Fat within the human body. Glycerol is simple, colorless, odorless, viscous liquid. And basically how fatty acids and glycerol basically interact is they actually are one unit as a fat cell. We'll talk about beta oxidation a little bit, but beta oxidation basically separates them again into 3 fatty acids and a glycerol molecule. So we can use those for energy and ATP production, but we can't use a fat molecule as it is. It has to go through beta oxidation. We'll talk about that in a second. Lipid structure. Lipids are composed of carbon, hydrogen, and oxygen, much like carbohydrates, but have twice as many hydrogen atoms. Fatty acids are chains of carbons linked together. One end, the fatty acid carboxyl group, which allows fatty acids to mix with water, which the other one is a methyl group, which does not mix with water, but it does mix with other fats in the body. Saturated fats, unsaturated and polysaturated fats. So as far as the saturation goes, we're talking about the ability of hydrogen atoms to basically bond to the molecule. The more saturated, typically or stereotypically, the worse off the fat is for you. Saturated fats are going to come from mostly your animal sources, and then you have unsaturated and polyunsaturated coming from mostly animal sources. Of the polyunsaturated fats, we also have the omega fatty acids that come as a subgroup from this. Omega-3 fatty acids promote anti-inflammatory properties as well as decreases in blood clotting. Omega-6 fatty acids promote blood clotting and membrane formation. Both are super important, so definitely getting in polyunsaturated fats is going to be a important health aspect, but saturated and just unsaturated fats also have their place as well. One backwards. Lipid functions. Lipids serve many functions in the body, including storing energy, supplying essential fat, absorbing, transporting fat-soluble vitamins, protecting and insulating vital organs, adding satiety to food and flavor, providing cell membrane structure, as well as serving precursors for several steroid hormones. When it comes to cholesterol, we have 2 different types, or 2 major groups. We have low density lipoproteins, or LDL. If you've ever got blood work done as far as cholesterol goes, these numbers will be fairly familiar. Low density lipoproteins form bile, can collect on the lining of damaged arteries. Typically going to be, or stereotypically bad cholesterol. It isn't inherently bad, but it could be, depending on the levels. You need both, but to varying ratios. High density lipoproteins, or HDLs. You can kind of remember the difference between the stereotypically unhealthy to healthy, with the little H being in the HDL. Think healthy. Inhibits arterial plaque formation, known as good cholesterol. Essentially, LDLs are not bad. Essentially, what happens is, if I can find my marker, which isn't okay, you have your artery here. And for some reason or another, I say some type of damage occurs. And now we no longer have a smooth, continuous surface. We have like a pothole in a sense. And we have LDL build up there. If it's a healthy amount of LDL, we have a nice smooth surface. If it's too much LDL, and like if someone from the city came out and just poured a truckload of asphalt in a pothole and didn't tamp it down, didn't smooth it out. Basically, it's just sitting there for things to basically collect in, and we can get a blockage essentially over time. That makes sense?
Yeah.
I always tend to like to talk about like a pothole because everybody can relate to potholes in the street. Especially in Houston, I live there, and a couple times I get new tires because of the potholes. Even though up here in Dallas, I feel like potholes in the highway sometimes, especially when I have my trailer and I see the trailer like bounce up off the ground there. I'm like, oh my God. Lipid intake and sources. Recommended intake for lipids between 20 and 35%, or in other words, 25 to 35% of daily calories, or 20 to 25 for athletes. 10% or less coming from saturated fat sources. And again, this is going to be our NASA recommendation. We have some sources here: meat, cheese, egg yolks, whole milk, etc. Unsaturated fat sources: olives, canola oil, peanuts, avocados, those sort of things. And we have polyunsaturated fat sources coming from soybean oil, corn oil, safflower oil, sunflower oil, salmon, depending on how you say it, flax seeds, walnuts, etc. And again, if you look in your book, you'll actually see a full chart of these things, as well as if you just search them on a lot of your logging apps, they'll also have if they're polyunsaturated heavy or monounsaturated heavy and those sort of things. Alcohol, not a macronutrient, but it does provide calories, so we have to talk about it. Basically, most people consume some at some point in the day or throughout the week. Maybe just me that does it daily. Alcohol provides 7 calories per gram. Alcohol is technically not a macronutrient, or needed in any quantity to stay in life, but does provide calories. Therefore, you are intaking energy. This energy source does not provide vitamins or minerals to contribute to the body's growth or maintenance. Although studies have shown that alcohol such as wine do have some intrinsic cardiovascular system benefits, they're very modest, and for the most part, it's very easy to tip over the point where they're no longer beneficial as far as the amount goes. So definitely not recommended to put alcohol in everybody's diet plan, but if they are going to have some, wine is probably the best. Moderation is always the best practice with pretty much any alcohol, but wine being the only one that has an intrinsic benefit at all. Okay. Then we'll go through micronutrients here, and we'll take a small break. Micronutrients. Okay, vitamins and minerals. Vitamins and minerals are considered micronutrients because they are required less than a gram per day to sustain life long term. They play vital roles such as extracting energy from macronutrients, producing hormones, and helping support oxygen to tissues in the body. Having a diverse diet full of bioavailable, nutrient-dense, unprocessed foods helps supply ample amounts of vitamins and minerals. But many people do not get this, so they do supplement with the multivitamins, but not all multivitamins are really some of the ways that the vitamins and minerals get synthesized and put into the supplements. It doesn't always get you in the best form for absorption. Multivitamins are great as a supplement, but should not replace eating those high bioavailability foods or the nutrient-dense foods. The best rule of thumb is to get it from a natural source, or worst case, a raw vitamin at least. Raw vitamins tend to have the most usable forms of most of the nutrients, but food can be the best way. Some benefits of phytochemicals such as fiber cannot be substituted. I can get the what's it called? The psyllium husk, stuff like that, like the supplements.
Mm-hmm.
But it's still coming from a food source. But it can't really be synthesized by humans as far as an alternative to actually consuming it from a plant source or a complex carbohydrate that produces fiber. It can be concentrated from a plant, but not be synthesized. As far as your supplementation goes, we have two different types of vitamins. We have fat soluble and water soluble. Water soluble are almost impossible to overdose on. The body basically purges them every 24 hours. They're only really in the body at a usable potency between 8 and 14 hours. And they can be dispersed through the body's fluids. Fat soluble vitamins are dissolved in the liver and the fat tissue and stored in the fat tissue. And they can stay there for quite a while, so it's very easy to overdose on them if you're taking them in excess. As far as water soluble, we have our vitamin C and all the B complex vitamins 1 through 12. You'll see a full list of these guys also in the chart in the book when y'all do y'all's readings. Fat soluble vitamins, we have A, K, E, and D are fat soluble vitamins. Minerals. Minerals are inorganic compounds made mainly of metallic elements, serve as constituents for enzymes, hormones, and vitamins. Minerals play an extensive role in the catabolic and anabolic process of the cell, assist with the synthesis of metabolic compounds, which enables the biological nutrient formation of glycogen, triglycerides, protein, glucose, fatty acids, amino acids. So obviously very important. Glycogen being those stored carbohydrates in the muscle liver. We also have the triglycerides being fat molecules, and all the other important ones there. Primary functions, providing components for teeth and bones. Calcium being a mineral, obviously important for teeth and bone formation. Also with muscle contractions. Cellular metabolism, actually the heart, muscle, and nervous system. Manages the acid-base balance in the body and also cellular fluid balance. DRI. Typically when we look at food labels, also supplement labels, we're going to be looking at the label for what percentage this is going to take out of my daily need of this thing. So when we look at the label, we have different levels of recommendation. We have the EAR, or EAR, estimated average requirement, the amount of each nutrient that meets the requirements of half of healthy people in a particular life stage and gender group. Recommended daily allowance, or RDA, the amount of each nutrient that meets 97% of healthy people in a particular life stage and gender group, obviously being the most accurate because we're talking about 97 instead of half. We have a bigger group there that obviously we're satisfying. Adequate intake, which is basically the bare minimum, AI. The average intake of each nutrient needed to sustain health based on studies of particular people in a gender group. Tolerable upper limit, this is where we get into toxicity. Again, mostly with our fat-soluble vitamins and minerals as well. Tolerable limit, or UL, the upper limit is safe daily intake for a nutrient. Take a little break. Right. Arguably, about 7 days you can. All right. About 7 days you can last without food intake, but only about 3 without water. So very important, obviously. Water is a part of nearly every metabolic process in the body. Human body is an average of 40 to 75, or 40 to 70% water, with the average of 60%. Water with about 70% of that being found in skeletal muscle tissue. Consuming too little water not only have acute effects on weight loss, but also sports performance and can be fatal. This is my least favorite thing I see people do is wearing the sweatsuits around. They don't understand weight versus fat loss, and they think you can burn fat off, and it's not the case. Making yourself miserably hot is not going to burn fat off, unfortunately. Just going to dehydrate you. If you're weighing for a sport or something, then great, use it, but performance is going to be lacking, so you got to use it in moderation, assuming that you're weighing and trying to lose that weight is not going to be close together, hopefully. I used to do that for powerlifting, but then it would hurt my performance, so it is what it is. But can also have effects on weight loss as far as being dehydrated. Water is involved in the process of breaking down fat and pretty much every metabolic process as we already mentioned, so it can definitely hurt weight loss. A nice hydrated body is going to be more of a fat burning machine than a dehydrated body. Water also helps regulate body temperature and the body's acid-base ratio, as well as blood pressure. Water is an inorganic substance, meaning it does not contain carbon. Consists of 2 hydrogen atoms and 1 oxygen atom. Bond is unique and allows for many substances to be dissolved in it. Water serves many critical functions of the body. It serves a medium by which the blood transport nutrients, water-soluble vitamins specifically, diffusing gas, gets rid of body waste, lubricates joints, cushions vital organs, and provides structure for skin and bodily tissues. Water also helps stabilize the body's temperature by absorbing heat generated by exercise and environment, then use the mechanism of sweating to diffuse the heat. Intake, incredibly variable for many people. We do have some super specific recommendation here, but really just drink so you don't feel thirsty anymore. It's going to be highly variable based on environment, level of activity, the amount of muscle mass you have, all sorts of things. Besides just drinking water, we do get water from some non-primary sources such as vegetables, things of that nature. But most of it's going to come hopefully directly from drinking water. Having caffeinated beverages that have a little bit of water in them aren't really the best source, because you may have still a net hydration gain, but it's going to be minimal compared to just having water by itself. As far as females go, we're looking at 2.2 liters a day, or 9 cups. For males, looking at 3 liters or 13 cups of water. For myself personally, I do a lot of outdoor work, so I just like having a gallon jug with me. It looks ridiculous sometimes, but it is what it is. Because a lot of times when I slam back like a small water, I tend to think, oh, I'm good for the day. But if I have that big old guy there, just kind of a constant reminder. A lot of people also put those little tick marks on there.
Yeah.
Or they also have jugs now, I think, that are refillable that have little tick marks and stuff like that. But I like old school. Plus, I don't clean stuff very well, so it'll grow like mold by the time I actually get around to cleaning it and find other issues for me. So as far as pre-exercise, about 2 hours pre-exercise, you're looking at ideally consuming 14 to 22 ounces during exercise, about 48 ounces for every 15 minutes, about 16 to 23 every hour. Post-exercise, 16 to 24 ounces for every pound lost during exercise. And a lot of these are oddly specific again. Just a reminder to drink regularly. Drinking during exercise does not inhibit any type of performance gains. It doesn't make you tougher to not have water, any of those things. So the more water, the better. Just make sure you don't gulp at the point where you need to throw up when you're doing your squats or something. use common sense. But post-exercise is probably the most important for me. Pre and post for the most part. Post-exercise, especially if you're working outside or you're doing exercise outside or in a hot environment, if you're in a CrossFit box without AC, or as I am, I'm in my garage right now with my my little setup in my garage, my road rack and everything. Definitely losing a lot of body weight through sweating in there. So if I want to have a nice hydrated rest of my day, I need to replace everything that I just put out. If the exercise is going to last more than 60 minutes, sports drink with up to 8% carbs should be used. If 25 or more pounds overweight, consume an extra 8 ounces per day when it comes to water. The best possible thing I would say is probably just making sure that with the water consumption, you're getting electrolytes. And we'll talk about electrolytes here in a second, but it's really easy to get oversaturated with water and be depleted of electrolytes, especially like sodium, for instance. Sodium seems like it's a bad thing, and it is when you're eating like French fries all day. But when it comes to water, water balance in the body, you need something to help the water stay in the body, and that's where electrolytes, specifically sodium, water balance is going to occur there. You need to have enough electrolytes to retain the water, or you're basically just constantly peeing out. So during exercise specifically, I would recommend a little bit of Gatorade or some type of electrolyte additive to your water or something. Doesn't have to necessarily have lots of sugar in it, but definitely going to help retain a little bit better. Balance or water loss. Hydration status depends on the balance between water intake and loss. Water loss depends on many factors, including temperature, humidity, and environment, age, intensity, duration, activity, and individual's fitness level. It's important not only for the athlete to perform, but also for overall health and monitor weight loss due to exercise. Water loss can happen through many ways. You can pee it out, sweat it out. It comes out through your breathing, through respiration, through your poop, and other what we call insensible water loss, which is like crying. Be very sad if you became dehydrated from crying, but I'm sure it's possible. Hydration. Dehydration. Dehydration can affect performance, threaten health, and extreme conditions of a person's life, even at 2 to 3% weight loss due to total weight loss. You weigh yourself essentially, and you've lost 2 to 3% of your total body weight. When you weigh again after your workout, you're definitely going to start feeling performance inhibitors. When electrolytes are lost, not replaced properly, the rate of hydration can accelerate greatly. So like I said, if you're not replacing those electrolytes, but only doing water constantly, especially if you're at 2 to 3% dehydration, then you definitely need to look into the electrolytes. Signs of dehydration: dry mouth, headaches, rapid heart rate. Obviously, as the water volume in the body goes down, the volume of the blood actually decreases, and you have to, the heart actually has to beat faster to get the same volume of blood to certain working tissues and organs. So you can have a rapid heartbeat. Sleeplessness, constipation, rapid breathing, thirst, unconsciousness, dizziness, fever, decreased urine output, sunken in eyes, confusion, dry skin, low blood pressure. All those obviously having varying severities. Dry mouth and thirst being probably your first clue there. I know doing a little construction myself, I know that when I'm on roofs and I feel a little dizziness, it's probably my dehydration kicking in. Electrolytes: minerals, potassium, sodium, and calcium. Potassium, sodium, calcium chloride, magnesium, and phosphate. make up what we call electrolytes. Electrolytes are help control the balance between fluid in the intracellular and extracellular environments and are essential for electrical conductivity within the body. Water typically follows sodium, so lower sodium intake means lower amount of water is being retained in the body. During periods of very low sodium and very low water levels, the kidney will upregulate water recycling and cause the body to retain water. This is due to the antidiuretic hormone ADH stored in the posterior pituitary gland and released by the hypothalamus. So this is actually something that when people prepare for bodybuilding shows and stuff, they struggle with. They don't want to underhydrate for too long to where we get the ADH to start being released to the point where we start bloating and looking soft, but you can see more striations when someone's slightly dehydrated through their body, but there's also there's a give and take there, basically. You have to figure out what water loading or water fasting they need to do. Why typically when you're doing bodybuilding shows, you have like a peak week where you test out these things and see how somebody's body reacts. Carbohydrates as well. As far as glycogen goes, glycogen has many bonding sites for water, so it can actually puff you up a bunch. But funny enough, like especially people going like low carb diets, we'll see that initial like 10-pound punch of weight loss. Mm-hmm. But a lot of that is actually those glycogen stores being depleted and those water stores no longer, those attachment sites for water no longer being there. So additional 10 pounds is a lot to do with the water loss. Mm-hmm. So if you never really get past 10 or 15 pounds on a low carb diet, that's probably what's going on there. Electrolytes lost through sweat, mostly sodium and potassium. Hyponatremia, loss of significant amounts of sodium, resulting in an increase in the person's water levels. Hypocalcemia, kalemia, results in the loss of significant amounts of potassium, resulting in weakness, fatigue, constipation, and muscle cramping. So as you mentioned before, sports drinks such as Gatorade are going to be a great tool to use for exercise that lasts longer than about 60 minutes of continuous activity. It's going to restore glycogen, muscle, keep blood sugar levels stable, as well as the electrolytes and the water content there will help hydration levels be maintained. Time it is today, see if we're doing good. Now we're actually getting into a little bit more functional nutrition as far as understanding what's happening with the carbs, proteins, and fats. Thermodynamics. First law of thermodynamics is energy can neither be created nor destroyed. Different, basically transferred into different forms. And kind of like the circle of life thing. If you've ever heard of the circle of life, basically what happens is, let's say you have we'll draw my marker. Got a guy here, he's eating a carrot. It looks like a piece of pizza, I guess. You got a guy, as he's eating his pizza, I guess he has a heart attack. And we got the guy laying on the ground. He's dead there, and then we got little worms that eventually eat him. And then from there, we basically create more topsoil and nutrients in the ground, and we get these wheat plants that basically grow, and then they harvest the wheat and they make dough for the pizza he just had a heart attack eating. So essentially everything kind of goes around the circle. So basically we consumed energy, we created ATP out of the food that we ate. We did a little bit of activity before we had the heart attack. And then when we die, or anything dies or decays, we basically become nutrients for something else. And our body energies can basically create something else, in this case, a field of wheat to be harvested to make pizza. It all goes around a circle. There's no loss of energy. Basically, it just gets transferred and transferred and transferred. Mm-hmm. Make sense?
Yeah, I like this.
Slightly morbid, but slightly morbid, but it is what it is. Although macronutrients provide calories, they do not directly provide a usable form of energy simply by their ingestion. After food is ingested, nutrients are absorbed, several chemical reactions take place before the food becomes usable energy. Chemical energy. Chemical energy is contained in a molecule but not yet released in the macronutrient. Turning the chemical energy into a form the body can use is requires several chemical reactions, which we call metabolism. Metabolism is the sum of both anabolic and catabolic biochemical reactions that occur within the body's cells, produce a usable form of energy called adenosine triphosphate. Metabolism is a term meaning a metabolic process that breaks down molecules into smaller units or breaks them down to be used in other processes. Anabolism is a metabolic process that actually builds up molecules. Being catabolic is a term that most people have probably heard, which you can kind of relate to this. Catabolic means breaking something down. Not necessarily a bad thing, but it means to break something down. And anabolism or anabolicness means to build something up, which again, anabolic is probably a term most people that lift weights have probably heard before. Anabolism being kind of a reference of that. Got some examples of that. Catabolism, breaking down glucose to form ATP, or breaking down glycogen with which is that stored carbohydrates in the muscle liver to again be pulled back into metabolism for ATP production and blood sugar regulation. Anabolism example, basically how the body uses amino acids to basically build up muscle tissue. Metabolic pathways, a series of chemical steps or reactions that either breaks down or builds up compounds in the body. Mitochondria is the part of the cell where the energy production pathways occur, site of most of the body's ATP production. Mitochondria, that's an important part. Acetyl-CoA, an important molecule in metabolism that is formed when as an intermediate in the oxidation of all macronutrients, fatty acids, glucose, become acetyl-CoA if enough oxygen is present and enters the mitochondria. We'll talk about the acetyl-CoA and kind of all the energy systems here in a second. Okay, energy systems. Energy systems are incredibly important to understand because if we don't understand energy systems, then we essentially will not know how we're supposed to prescribe rest periods, intensities, durations, all that fun stuff. And all the exercise programming comes back to understanding energy systems, because if you're working someone in a energy system that they don't have nutrition for, or if you're trying to work them in a energy system and you don't understand rest periods and that sort of thing, then you're going to be working around in circles, making your plant miserable. The pathway by which ATP is produced depends on the availability of oxygen in the cells. The ATP phosphocreatine system is where we use individual ATP molecules for energy that are already stored in the cell. So let's actually start a little diagram here. I call this one, it says the phosphocreatine system. This is what I'm going to be calling the ATP PC system up here. So just a right. So this is the energy system used for about 10 to 15 seconds of effort. So like power cleans, like 3 to 5 reps power clean, maxes, things of that nature. Things that are short and intense in nature. And then if the exercise continues, then we move into the anaerobic metabolism. And the anaerobic metabolism is going to be pulling from glycogen stores. We also call this the glycolytic energy system. This is when we hadn't yet introduced oxygen yet, and then we have the aerobic. If fat, carbs, and oxygen being introduced in this energy. So the anaerobic energy system, or the glycolytic in other words, is going to be used when we have exercise going on that is less than 3 minutes. And then we have the aerobic energy system kicking in somewhere between 2 to 3 minutes plus. And there is going to be overlap. So there's not just a all or nothing when it comes to these energy systems here. You're going to start off with your, well, let's back up just a little bit. Aerobic, also called the oxidative system here. The aerobic or oxidative system is actually what we use at rest as well. So right now, when you're sitting in seats, you're using the oxidative energy system, primarily utilizing fat at low intensities. As soon as we grip that bar and start moving, then we're moving into the ATP-PC system or the phosphocreatine system. Then we're going to be moving into the glycolytic energy system or anaerobic energy system. And this is mostly going to be like our bodybuilding range. When we're doing our 10 to 12 repetitions, 8 to 12 repetitions at a moderate tempo. And then over here is going to be where we're doing long prolonged exercise, whether we're doing like a circuit routine or we're doing a 30-minute run on the treadmill or a 30-minute jog on the treadmill. Something that's long and sustained, in other words. And the higher intensity that we use, the more carbohydrates that we will use in the oxidative system or the aerobic energy system, in other words. As intensity increases, more carbohydrates will actually be used. Anything mentioned so far?
Can you explain that the more intensity increases, carbs will be used?
Okay.
In this one?
Yeah, that's exactly what I was about to expand upon. I just
Okay.
wanted to make sure you were there with the deal here. Okay, so with the aerobic or oxidative system, now we have oxygen, in other words, being able to get in the mix, and now we're able to do beta oxidation, which breaks down fat. It separates the fatty acids and the glycerol molecules, so we can actually utilize it for ATP molecules. As we increase intensity, we use a higher percentage of carbs. So one would think in your head, well, why don't we just say the low intensity and have mostly fat burn, right? However, the fat burn at rest when we're starting out is super low. However, when we get to this energy system through continuous exercise, especially when it gets more intense, you're going to be burning a very large amount of calories. So it's like these aren't real ratios, but let's say we have 90% of this little bitty amount of calories here. Let's say out of the 5 kcals you're going to expend in this situation, 90% of those are going to be fat from calories from fat.
Mm-hmm.
However, let's say we have 250 kcals burned over here, and only 25% of that is coming from fat, but 25% of 150 is going to be a lot greater number than it's going to be 5 calories.
Okay.
Even 90%. Does that make sense?
Yeah, that makes sense.
My laptop keeps hitting it or it keeps bumping it down. Hopefully everybody on the videos at least heard me if they didn't see it. Yeah. Essentially, the higher intensity that we have as far as effort goes in the energy systems, even though a smaller percentage of fat's being used, and that's what most people are looking at is fat usage, obviously.
Mm-hmm.
Overall, I thought that was your backpack. 90% of 5 calories is going to be a lot less overall as far as fat loss than we have 25% of, say, 250 calories, because of the fact that at rest we're not burning many calories, but at a high intensity we burn a lot of calories. Mm-hmm. So even if the percentage is less, we're still overall burning more calories from fat. An HPPC system, short, powerful contractions, and we can use those for like 1 rep maxes or short bursts of energy. Mm-hmm. Typically, also like powerlifting, we would use this. Thing with this energy system, though, is that we have to have about 2 to 5 minutes to recoup everything 100%. So for the ATP-PC system, we have to have a longer rest period to have it 100% again. With the glycolytic or anaerobic and aerobic or oxidative systems, it's using stores of energy that are readily available. Carbohydrates, we have those 300 grams stored. With fat, relatively unlimited amounts of fat, depending on how much body fat you have. It's always going to be available. So with these guys over here, the rest periods are slightly less important in terms of having energy available. Mm-hmm. However, the ATP-PC system, the more powerful one here, the short-term more powerful one here, has to get those ATP molecules back into the cells for that sudden burst of energy still. And the ATP-PC system is actually very interesting because even though there's a small amount of ATP in the cell, it actually uses like a recycling system. So for the first 5 seconds or so, it's going to be utilizing pure ATP, but at a certain point, it's going to use up all the ATP molecules. So you're going to have a bunch of what we call ADP. Instead of triphosphate, we have diphosphate molecules. So essentially, we'll go up here. We have a triphosphate. Got 3 P's up here. You have a muscle contraction. And now we have a ADP, which is not usable. So what happens is we have a phosphate molecule that comes in, re-energizes it back to a triphosphate molecule, and it kind of recycles.
Oh, okay.
But as far as the amount of energy being used for that short, intense effort, this is not going to be something the body can keep up with for very long, and that's why we get the 15 seconds where it starts to taper out. And like I mentioned, everything's kind of like a gradient here. Everything overlaps. There's not a stop and start point that you can really pinpoint when you're using these energy systems. You can kind of tell when you're inefficient at using one energy system, but it's not going to be like, okay, I got to wait for the next energy system to kick in. Come on, come on. Like, you're not doing that. Like, it's a gradient into it. But you'll notice that when you work in an energy system very frequently, you're going to get there easier. It's going to feel more fluid. Some people definitely have a hard time getting to the oxidative system, especially if they haven't done any endurance sports and they're trying to get into like endurance stuff. They can definitely feel when they get into this. It's kind of like the second one. It's kind of like that runner's high situation where you're getting into a point where it's getting a steady flow of energy going. Because from here we're looking at when we break down a molecule of carbohydrate, we're getting about 36 ATPs. Over here, I believe it's 441 when we talk about breaking down fat molecule. So over here, we got a good little amount, but it's going to peter out really fast. Over here, we have a stockpile, but we just have to get to that stockpile.
Okay, wait. So a carb is 36 ATP, but a molecule.
I believe that's right. I'm gonna have to.
Or something close to that.
Yeah, have to do that. Am I right on that one? I know it's here somewhere. Come on. Should be in parentheses somewhere.
Is it this one? 36.
Is that? Yeah, 36 is definitely right. I'm trying to think of the fat one. I think it's 441. Super sounds right in my head. Okay. We'll get here in a second. So again, back to the glycolytics. So individual ATP molecules down here. We got our 36 when we break down the carbohydrates. And then when we get past the past that point, we get into the aerobic energy system or oxidative system. Now we have fats and carbs to pull from. And when we get that fat broken down, the 3 fatty acids and the glycerol, we have a stockpile. So that's why we can come into the oxidative system or aerobic energy system and keep on going. It seems like almost forever because now we have the stockpile. We can just keep on burning this fuel, but you can only keep up so long with the 36 ATPs, and for sure when you're just using individual ATP molecules that are stored in the little cells, they can only keep up so long. So, but for the most part, bodybuilding, gaining muscle tissue, we're looking at somewhere between the ATP PC system, the phosphocreatine system, and the glycolytic energy system or anaerobic energy system. Maybe slightly into aerobic, but this is going to be a main bodybuilding style, and this will be mainly endurance for the most part. So the next little slide here, we're talking about the respiratory quotient, or RQ, the amount of O2 expired divided by the amount of O2 consumed. So essentially, the harder a person works, which again, the more they're getting into the facts, the more they're getting into the aerobic or oxidative system, we're going to start utilizing both fats and carbs. So when this is sustained, we start to see fat consumption, and as we see intensity increase, we start to see the carbohydrates now take the primary role of being the fuel provider, because the carbohydrates take less processes to break down. You're going through just a handful of processes when it comes to the ATPs. You're going through 2 or 3 handfuls of processes to get the fat into a usable form. So it makes only sense to start utilizing carbohydrates as the primary fuel source after a certain amount of time and a certain amount of intensity. But again, on this, even though we see the larger quantities of percentages, note that the overall calorie burn, no matter what, is increasing exponentially with each raise in the respiratory quotient. So even though at 0.95 value on the chart there under the RQ, even at 16% from fat is going to be a much larger number than the 100%, anywhere from 70% below. Now we're going to talk about carbohydrate utilization, and really we're going to talk about all the macronutrients being utilized, kind of the process it goes through. This is something you won't necessarily have to remember. Honestly, on the NASM examination, the nutrition part is very sparse. But since we do offer a nutrition coaching certification through the course, we do want you to have a little bit more of an advanced knowledge. The cell, glucose is broken down via the chemical process, metabolic process called glycolysis. Glucose will go through many reactions to, in glycolysis, ultimately become the process called pyruvate. These not requiring oxygen to take place. Throughout this process, glucose changes forms and ultimately becomes ATP. If enough oxygen is present, once the glucose has become pyruvate, it enters the mitochondria for aerobic metabolism and becomes acetyl-CoA. Many steps in the aerobic process can go either direction, but when the pyruvate becomes acetyl-CoA, it cannot go backwards. Acetyl-CoA starts in a pathway called a Krebs cycle, or TCA cycle. Tricarbonyl, I never say that word. It was a gamble. This process requires oxygen and produces 36 ATPs, as we mentioned before. Again, we only get in that Krebs cycle if there's enough oxygen present. So if we're in that aerobic metabolism. If not enough oxygen is available, such as when you first start exercising, a substrate called lactose is created from the pyruvate, providing some ATP, but relatively few comparatively. Fat utilization. Fat's stored as triglycerides in the body, in other words, in your fat cells. Therefore, the first step in converting ATP is to break it down into the triglycerides into the fatty acid glycerol, which I mentioned several times. Glycerol can be converted to pyruvate or glucose in the liver. That fatty acids must be broken down a pathway called beta oxidation, process where enzymes break down carbon chains that make up fatty acids, 2 carbon atoms at a time, convert them into acetyl-CoA, working into the Krebs cycle, presence of oxygen. Acetyl-CoA joins with oxyolactate during the process of the Krebs cycle. I hate saying these big words. Oxyolactate, we're gonna go with OAA, is a crystalline organic compound made of carbohydrates that is a metabolic intermediate in many metabolic processes. When carbohydrates intake is low, the Krebs cycle slows due to a lack of OAA. If this is prolonged, the body will form ketone bodies, which will be used as an alternative fuel source. The body prefers to use carbohydrates, but it will use ketones as a supplement for that or an alternative. Under normal circumstances, protein and amino acids are not used for a large extent for energy. However, during starvation or when carbohydrate supplies are limited, amino acids can be used to make ATP. Definitely not preferable, lowers your metabolic rate, so obviously, for the most part, bad. First step in breaking down amino acids is to remove the nitrogen group, which I explained earlier is basically a waste nutrient in the body. Do a process called deamination. It's converted it into urea or P, in other words, and excreted. Deamination, first step is to break down the amino acids. This includes the removal of the nitrogen group. Once the nitrogen is removed, the carbon skeleton is all that remains and has the ability to enter energy-producing pathways at different spots. So it can be used very flexibly. Carbon skeleton is the structure of an organic compound, series of atoms bonded together that form the essential structure of a compound. Basically like that spiral staircase that you see in anatomy pictures or in can't think of the class. I guess maybe chemistry or anatomy class. Anyway, anywhere where you see like a DNA strand, essentially like a double helix, the spiral staircase is basically what it would be referencing. Depending on the amino acid, carbon skeleton, where it came from, it can enter as pyruvate or acetyl-CoA to different places in the Krebs cycle. Creating and storing energy. Carbohydrates and storage creation. About 400 grams of glucose can be stored in the liver and skeletal muscle. I aired you earlier. I said 300. I was thinking of just the skeletal muscle. It's 400, so 100 basically in the liver, most of it being in the skeletal muscle at 300 grams. And that's also at a very high performance level. It doesn't necessarily mean that the body is storing 400 grams at any time and place. Mm-hmm. That's under best conditions with good nutrition. Okay. 400 grams of glucose can be stored in the skeletal liver and the muscle. It was a rough morning already. In the liver and skeletal muscle in the form of glycogen and can be released by glucagon, released from the pancreas. Glucose can be created as well in a process called gluconeogenesis, which can use the breakdown of amino acids, lactate, glycerol, and pyruvate to create glucose. They're very flexible. Gluconeogenesis is the formation of glucose from non-carbohydrate sources such as amino acids or fat byproducts. Fat storage and creation. Fats are stored mostly in the adipose tissue or fat tissue, fat cells. the small amount in the muscle tissue. Fats are produced in a pathway called lipogenesis. Anything that can form acetyl-CoA can also be converted as fat stores. The fats, carbohydrates, alcohol, and amino acids can all become fat on the body. Protein storage and creation. Proteins do not have a large capacity to be stored in the body. The small amounts of amino acids, called the amino acid pool, can be stored in blood and cells. The body can make non-essential amino acids, from carbon skeletons it gets from pyruvate, essential amino acids, even the breakdown of the body's own tissue as to break down skeletal muscle to service it. Okay, so I think we have, yeah, we'll have enough time here to go over the FTA metabolic calculations. So again, this is going to deviate from the book. So this is not going to be in the book, most of it. When we have NSAM references, we're going to say NASM references, and when we say FTA stuff, it's going to be what we're going to need on the final project and what we require to learn for our nutrition certification.
Okay.
Which this is probably the funnest part of this, because this is actually the functional part. All the other stuff is kind of just noise. And now we're actually getting into how to actually use all this information in a functional way.
Okay.
I'm going to erase all this because all going to get in the way. Y'all didn't have to take the exam. We could literally skip all of what we just did. Okay. So, RMR, resting metabolic rate. Is going to represent about 70% of the caloric expenditure that you have during the day. And that basically means sitting there, your bones, your muscles, your organs, all those things require energy to sustain themselves, maintenance, growth, etc.
Mm-hmm.
It's actually 60%. But anyway, a very significant amount, in other words. The other the other 40 to 30% being anything that you voluntarily do throughout the day. So still significant, however, not quite as significant as the muscle and the organs and the tissues, what they're burning just being themselves.
Mm-hmm.
So as we can see from this, if we had more muscle tissue to maintain, it would raise our resting metabolic rate, and it would be the most efficient way at increasing one's metabolic rate and burning more calories. So the more muscle you have, the easier it is to lose weight, the more you can eat, all those fun things. Activity and exercise are obviously going to complement that. However, it's a less efficient way to prioritize things.
Mm-hmm.
What I personally recommend is kind of like a retirement plan in a sense. We were talking about that earlier. We both have a financial accounting background.
Yeah.
So with the exercise, it's really supposed to be kind of an investment in a future amount of muscle mass when it comes to the metabolic rate. The more muscle you put on the body, the more you can eat and still maintain a certain body fat percentage. But it's not going to happen overnight. It's going to happen over years and years of constant work. However, once you get to that point, you basically have a passive income stream of calorie burning in a sense. It's something you don't even have to think about, but you're burning more calories because you have more muscle tissue. Activity is still going to be important though, for multiple things, not just your functionality and bone density as far as weight bearing exercise, all those fun things, but just keeping moving around is also going to give you somewhere between a 40 and 30% extra amount of calories that you're burning. If you didn't focus on building muscle, then you would have to focus a lot more on the exercise where, I mean, that's a lot of effort to put forth. I mean, if you could literally just burn calories by consistently working out at a moderate level instead of having to like do a exorbitant calorie burning workout every single day versus just letting your body naturally slowly gain muscle tissue, it seems a lot more efficient to me long term. It also makes it easier to lose weight in the future because you do have more muscle mass and you can't eat more. You don't feel like you're starving yourself. Mixed in with that, you also have the thermogenic effect of food, the TAF. Thermogenic effect of food is actually the amount of calories it costs or the amount of calories it uses to essentially process the food and get it to the place it needs to go. That being said, when we look at the thermogenic effect of food, it's a very small percentage, so definitely don't count on that to hang your hat on as far as weight loss goes. When we talk about our equation, we really don't take thermogenic effect of food into account. Because really when we do metabolism, it's really just kind of a science experiment in a sense. We're taking a very educated guess and a starting point, and then we kind of adjust from there with constant regulation and reassessment. So we're going to cover two different equations today. One's going to be the equation in your NASM book, which is going to be taking the body weight in pounds, multiplying it by 10 calories, and you get a resting metabolic rate. We also have some activity factors. The more active you are, you get more calories throughout the day to meet your TEE, which is total energy expenditure, which we'll see that definition next. But for a sedentary person, we're going to multiply the RMR number in the NASM equation by 1.2, essentially, 1.2 to 1.3, depending on the level of sedentariness. If someone's super sedentary, it's closer to the 1.2. If someone's, I don't know how you can be slightly less sedentary, I guess, it's kind of a fine line, to 1.3. But essentially what that does, it multiplies it by 100 plus 20%. For those that aren't good with math, that's what it does. As if you multiply it by 20%, then you're going to get 20% of the RMR, and then you're going to have to add it back to the RMR, so it's just one less step. So if you're on the calculator, whatever you get for the RMR in the NASM equation, multiply it by 1.2 or 1.3 for this example. Low activity, you're looking at 1.5 to 1.6, which can adding 50%, adding 60%. Active, adding 60%, adding 7%. And then we're looking at heavily active, we're going to 9 to 1.9 to 2.1. Personally, I'm not a big fan of the equation just because it doesn't take into account fat-free mass or fat mass. It's literally just taking this person at 200 pounds and didn't have any leg muscles and trained legs. And NASM says same RMR. Yes, they probably have different activity levels, so it does change things a little bit. However, that equation doesn't take into account anything as far as body fat goes, so it's not a big fan. I'm not a big fan of it. So we personally use one that attacks the body fat situation. So for the FTA equation, let's we got the NASM equation just for reference up there. And then we have what we use, which is Fat-free mass in kilograms, which if you don't know how to get things in kilograms, it's going to be fat-free mass in pounds. Divided by 2.2 equals a kilogram. So most of the scales that you're going to use, you can put in pounds. So on the pounds of fat-free mass divided by 2.2, and then we get kilograms. And then we're going to multiply 1.3, which is the estimated average calorie burn for 1 kilogram of muscle per hour. And then the 24 is 24 hours in a day. So we're going to end up with RMR that takes into account fat-free mass, which is bones, organs, everything that utilizes calories to maintain itself, but not the fat mass that actually is energy itself. And that's the big difference there in the equation mentality there. Rewrite this. Well, finding fat-free mass, how do we do that? So to find fat-free mass, we first have to know someone's body fat percentage. Don't know what goes to what.
Okay. Thank you.
I don't even know if I even okay. So we have fat mass and fat-free mass. Fat mass is going to be exactly what it is, fat mass. When we do the skin fold calipers, when we use the BMR, sorry, BIA, wrong acronym there, and we get the body fat percentage, we're going to utilize a equation that's going to take away the fat-free mass, and then we're left with only the fat mass. I'm not a mathematician, that's why I have Excel and calculators. So. Let's make it easy there. We say we have this small little person at 100 pounds, and they're at 25% body fat. Math's pretty easy there. 25% of 100, 25 pounds. And then we have the remaining bit, so 25 out of 100, you have 75 pounds left. 75 pounds is the fat-free mass. And this isn't the equation that's below, guys. If you're watching this video, this is not the equation below. This is a generic equation. So from here, we're going to divide by 2.2. Comes to the 75 fat-free mass. And we're going to get roughly 34. 34.0909091 to be technical. So right now we have kilograms of fat-free mass. Okay. So let's actually dump this right now just for the sake of utilizing what's in our slides here. Just want to give you all an example. So in our example there in the slides, you have a 220-pound male at 21% body fat. We multiply that 220 pounds by 0.21, which is basically 21% in a fractional form. Or sorry, in a decimal form, not fractional form. We get 46.2 pounds of fat mass. We take that out of the total 220 pounds, and now we're getting back to 173.8 pounds of fat-free mass. We still have to get it into a usable form, so we're going to take that 173.8 pounds of fat-free mass divided by 2.2 to get into kilograms. As you can see there at the very bottom of the screen there. And then we're going to multiply it by 1.3, which is the estimated caloric expenditure for 1 kilogram of muscle, and then multiply it at 24 hours for 24 hours in a day. And we get 24.64.8, or rounded up to 24.65, as far as the estimated resting metabolic rate. Are you following along? It's easy for me to pander to the video, so I want to make sure you're getting there too. Like if you have a math brain, you have like a workflow brain, it's pretty easy to do. As long as you have the steps, you can kind of reproduce it over and over. And we also do, for everybody on the video and you as well, we have a spreadsheet. It's not as pretty as the spreadsheet you've shown me, but there is a spreadsheet on the Google Classroom under materials that you can download. It'll do the automatic calculations.
Awesome.
There's a little bit of manual entry though. It's not super automated, but. So activity multipliers. So as I mentioned, versus the NASA, we have a little bit different multiplier system because we do take into account fat-free mass. We're gonna have a little bit different multiplier system here. So for the non-active people, we're sedentary. In other words, no exercise, sedentary job. We're looking at a multiplier of 1.25, or in other words, RMR plus 25%. For active individuals, looking at RMR plus 35% or 1.35 as a multiplier. Very active, 1.45, or basically the 45% on top of RMR. So you'll notice here in parentheses, after example, to the right of it, 21% body fat says active. So we're continuing on with that example there. Active, we know that's a multiplier of 1.35. So we're going to take that rounded up number, 2465, as far as the RMR with the FTA equation. We're going to multiply by 1.35, and we get 3,327.75 calories, which again, we're going to end up also rounding that eventually. Total energy expenditure, or TEE, is an estimated amount of calories your body expends throughout a day to maintain its lean mass as well as the activity levels. So RMR times activity multiplier will equal your TEE. And again, the TEE here is about 3,300 plus. Adjusting for weight change. So gain or losing weight. Adjusting one's weight for weight loss or weight gain should be a gradual process. Add or decreasing calories, recommend 200 calorie chunks at a time. Enough to cause change, but not enough to accidentally overshoot too much. And we'll talk about why that's a bad thing in a second here. When we talk about 200 calorie increments, ensures that the catabolic properties of the metabolism aren't going to catabolize the muscle tissue, but we also don't want excessive amounts of fat tissue to be formed if we're gaining calories either, or so we're trying to gain weight either, because it can cause bad things with testosterone and all sorts of bad things, but testosterone being one of them. For the most part, we're going to do these 200 calorie chunks as far as increasing or decreasing, because most people don't come to you and say, hey, I just want to stay the same weight. They say gain weight, lose weight, and there may be different verbiage used, toning, getting more muscle, some verbiage they use, but essentially it's either going to be gain or losing weight. When we look at the science behind weight loss, we have a pound of muscle weighing 2,500 calories. Not weighing, but being 2,500 calories as far as the energy value. And for fat, roughly 3,500 calories. So we know when we were looking at our calorie values for eating protein, eating fat, we know that fat is going to be much more dense as far as calories goes than muscle tissue. And it holds true when it comes to your body as well. So when we talk about weight loss, we're usually talking about week-long increments. So if we divide this by 7 days, which is a calendar week, we're going to get roughly, and change there, but roughly 357 calories per day. And you would have to add to your diet to gain 1 pound of muscle a week, to have the building materials in excess to have an extra pound of muscle be created. £1 pound. And for our fat, to lose 1 pound of fat, we would have to decrease our entire calorie intake after our TE measurement by 500 calories. However, this is not an exact science. You're always going to lose a ratio of fat and muscle, unfortunately. And the more severe the caloric deficit, the more chance that you're going to be losing muscle tissue. So, as I recommended, we do 200 calorie increments, even though it's going to be less than your pound per week up here. It's going to be the safer way to go about it, because we can ask these guys to do diet logs. We can ask them to do whatever type of tracking system you want, but there's a good chance that they're going to leave something out, they're going to lie, or just flat out not do it as far as telling us what they have been doing. So just cleaning up their diet, getting them back to their TE may be what they just needed. But when we're taking away calories, you want to be very, very careful, either taking away or gaining calories in someone's diet. We want to monitor them so that we can figure out where the tipping point is and then continue that direction in a small, planned way. Because if we take away 1,000, 2,000 calories from this person, there's a good chance that we're going to be gaining, so we're going to be losing a lot of muscle tissue, which is going to lower the metabolism quickly. Same thing if we give them a lot of extra calories, if they want to gain weight, we're going to gain a lot of fat tissue. But unless we have the exact right variables to gain muscle, we have all the anabolic things that we need. We're working out the right way, or we're doing the rest periods, we're in the right energy system. Infinite amount of things that have to go right. There's no way that we're going to be gaining a regular 1 pound of muscle per week. So we're going to be gaining a lot of fat along with that little bitty muscle that we're building. That all make sense?
Mm-hmm.
Okay. It's hard to pander to you and the camera at the same time. I think we're getting through it. One of the things I like to draw up here is kind of how I see weight loss or weight gain in a sense. And I always relate it back to plants. I'm not a huge gardener. I have the most brown, blackish thumb you'll ever see. But or something.
Nice.
Okay, we got a flower here. It's in the ground. Okay. So right now the flower is at an equilibrium or a homeostatic state. Basically everything's good internally, externally. Getting water. It has nutrients in the soil. It's super happy. Got a happy face on it. Now all of a sudden, we take away the sun up there, and oh no, we lost the leaf. We have our nutrients in the soil, but now we don't have any water. We have an unhappy flower here. Essentially, the flower is going to stop producing leaves. It's going to stop producing extra flower buds. It's going to stop growing. It's actually going to catabolize unneeded structures on the plant to deal with the amount of water it can actually intake. And the body does the same thing. The body will actually catabolize muscle tissue to bring yourself down to where you're eating as far as the calories go. So if you're eating 2,000 calories and now for the next 2 months you eat 1,500 calories, you're going to resemble what that 1,500 calories is going to look like. So essentially, you're going to catabolize muscle tissue to get down to that rested metabolic rate. Your RMR is going to be lowered by your body's self-preservation systems. I guess we don't really need an extra step. But this is kind of my weight loss thing to tell people, because if a plant maybe skips one watering, nothing really happens. But if it continually happens, then the plant basically wilts, it kills off things. But I feel like thinking about it in this term kind of helps people understand what they're doing as far as putting people in large calorie deficits or putting themselves in large calorie deficits. If it seems like an anomaly, the body's not going to adjust, but as if it seems continual and it's a very large, jarring change, the body's going to react in a self-preservation way and going to lower that metabolic rate by catabolizing muscle tissue. Hopefully that makes sense. I only say things and hope it makes sense to people. Makes sense up here. But I really can't preach it enough, but we just have to take an educated guess and then move forward with constant assessments. I would say your first assessment, I would wait 2 to 3 weeks at minimum. That is because there's going to be a lot of fluctuation. We're going to have carbohydrate depletion, maybe. We're going to have the body adjusting to exercise sometimes. People will upregulate glycogen stores if they haven't been very active, and so will actually retain more water. I've seen people gain up to 15 pounds first week of working out just because they're hydrating more, they have more glycogen stores, and they're freaking out. They're like, I'm becoming the Hulk. They're just freaking out. Crazy. Like, oh my God, I'm gaining muscle so quickly. I'm like, no, just water. But I like to wait about 2 to 3 weeks for my first weigh-in just to make sure we have something concrete. Because nothing's worse than starting with somebody that already, when people come to you, it's always at their lowest points, like, I've tried on my own. Here's my money, do something for me. Yeah. You don't want to come back to them, oh, well, good and bad news. I was able to pay my rent, but your weight went up 15 pounds. That's not something you want to go with your client with. You want to go with some solid measurements. That being said, we'll talk about what client expectations and spinning things different ways in the assessment section, but that's one way with the nutrition, just to make sure you're not shooting yourself in the foot. Assumptions and flaws. Without very expensive testing, all these calculations are just estimates of TE. That's exactly right. They're all just estimates. So whether you decide to use the NASM or the one that we're teaching you here going forward as far as the equation goes, they're all just essentially just estimated starting points, and then we just constantly monitor from there. We have to assume our body fat testing measurements are accurate. Our client has disclosed all medications, conditions, and we know about all genetic predispositions that might affect the metabolic rate. Talked about in the red section whether you've gone through it or haven't gone through it. We talked about the thyroid and how thyroid issues can mess up so much that you have going on there. Low testosterone, high estrogen, all sorts of things. Clients must be honest about their activity level and utilize the right activity multiplier. Can't tell you how many times I've heard vigorous gardening brought up when I talk to my clients. If you can't have a measurable system to indicate volume or intensity, then I don't call it exercise. Yes, activity outside is great, but if you can't quantify it, then I just classify as general activity. I don't quantify as exercise.
Yeah.
So vigorous gardening is not a thing for me, unless that's your job and you're doing it every single day. Certain medications also been shown to affect RMR. Cardiovascular medication can lower RMR by 4 to 12%. Chemotherapy could lower it by 11%. Long-term human growth hormone could raise it by 12%. Thyroid medication could raise it as much as 17%. All sorts of things that can throw your measurements off. So constantly reevaluate. And you're also not a dietitian, so if you get stumped on just getting recommendations, then you can also refer to a dietitian or nutritionist. Definitely recommend networking with a dietitian or something of that caliber to refer troubled clients to, especially if you don't feel comfortable giving recommendations if they have a special condition or pregnant or certain things you just don't feel comfortable with. Okay, now we're getting down to macros. Macros are probably the thing that most people get intimidated by. I would say it's arguably easier than the estimating the calories, but you can't really mess up someone's weight loss or weight gain with macros in a sense, because as long as the macros add up to the number of calories that would cause weight loss or weight gain, you're still going to get a result. However, macros are definitely where we get down to how someone feels or they're performing, kind of the details in between, in other words. So as far as our recommendations go for our equation, protein between 2.2 to 1.3 grams per kilogram of fat-free mass. So again, we want to keep that fat-free mass number of the muscle tissue readily available for this calculation here. Carbohydrates, roughly about 60% of the remaining calories, and then fat's going to be 40% of the remaining calories. So note that we're going to be taking the protein out first. So there's going to be a chunk taken out of that calorie recommendation, because the calorie recommendation is going to be either 200 up or 200 down, or it could be the TE, I guess. It could be right at maintenance level. Maybe we're just seeing where they can get back to their set point, see what happens first. But either 200 up, 200 down. That recommendation, we're taking away that protein recommendation, and the remaining amount is going to be our carbohydrates and fats. And people have a hard time with this, so I'm going to go ahead and do a little pie chart here. Let's say we have 1,000 calories, and we've taken out 300 for protein, readily theoretical. Then we have 700 left between carbs and fat, so 60%. Does that visual make sense for you?
Mm-hmm.
Okay. Protein's already gone. So out of the 1,000 calories, 300's gone. We don't factor that into the 60-40. That being said, 60-40 is not the end-all be-all. It's kind of a starting point. It's kind of a mid-ground. If a person is more active or less active, as we talked about with carbs, the recommendation goes up and down. There's actually a way that we can back check this as far as making sure that we're lining up with the NASM recommendations. We talk about grams per kilogram of fat-free mass or body weight, or if we're talking about between 40 to 60% of total diet, we can actually back check that with this equation. We can actually utilize both situations. So we have that. So we're going to do an example here. Okay, so as far as going through the macros here, we're going to go through a full example of a 180 pound female example at 23% body fat with an active classification. Her goal is to lose weight. So first of all, we're going to go through the resting metabolic rate calculations, get her T, and also get the recommended intake or RI. So 180 pounds times 23% as a decimal form gets 41.4. Then we move into the fat-free mass. We subtract out that 41.4 from 180. We get 138.6 pounds of fat-free mass. We're going to plug it into the equation. So 138.6 divided by 2.2 gets us into kilograms. And then times 1.3 times 24 equals 1965.6. And you can really start rounding at any point. I kind of round whenever I want to, really. I mean, a couple of calories here and there aren't going to totally mess up your calculation or anything. But just do it consistently the same way every single time. 1966 rounded up times 1.35, which is our active classification multiplier, gets us to 2654. She wants to lose weight, so we're going to take away 200 from that, so we get 2454 calories. For the macros, we're going to start with protein, as we do always. With the protein, we have a range between 2.2 and 3.1 grams per kilogram of fat-free mass. So we're going to take our pounds of fat-free mass divided by 2.2 to get in kilograms again, and then we're going to multiply by 2.5. So 2.5 is kind of the middle of the road. It's not 2.2, it's not 3.1. 2.2 being really small, 3.1 being really high, being right in the middle of the road there. For weight loss, you definitely want a good amount of protein, but you don't want to go overboard like you might with a weight gain goal. But you do want to have enough of the amino acids flowing in that if there was a period of starvation or a lack of nutrition, that we wouldn't catabolize a lot of muscle tissue. And we are going to be working out, so definitely need a upregulated amount of amino acids to help repair as well. So when we get to that, we get 157.5 grams. We need to convert that into calories, so we're going to multiply by 4. We have 4 kcals per gram of protein, so we're going to multiply by 4. We get 630 kcals. So now we're going to take that 630 we've already utilized for protein. We're going to take it out of the RI. So the 2454 minus 630, we have remaining 1824 calories. Of the 1824 for carbs, we're going to multiply 60%. We're going to get 1094.4. And then we're also going to divide that number by 4 to get our grams. So then we're going to move down to fat. So with fat, we go back to the 1824 times 40%. Now we've utilized 100% of the remaining calories. That 40% is going to equal 729.6 kcals. And if we divide it by 9, remember, fat has 9 calories per gram, we get 81 grams. So that's kind of your workflow there. I know it gets confusing moving back between calories and grams. I highly recommend utilizing a spreadsheet for this. We do have a spreadsheet on the Google Classroom under materials that I highly recommend you use or make your own, one of the two. But as long as you get this workflow down, it becomes super easy. It's just getting the workflow down so that you don't get your calories and grams and your RI and your calories after protein all mixed up together. Okay, so now we got a weight gain goal. So same person with weight gain. So we're gonna go through all the steps again, all the steps. And then at the bottom there, after TE, we're gonna add 200 calories. Again, being very conservative with this to make sure we know where someone's tipping point is, whether they're starting to gain muscle or weight in general, or we're losing weight. Protein, we're gonna be a little bit more aggressive on this one. So we found the kilograms of fat-free mass, but now we're multiplied by 3, which is a little bit more aggressive. That brings us up to 189 grams, and then also brings us to 756 calories. So from there, we're going to move into carbohydrates. So we're going to need to back out the kcals from the protein. We have remaining 2098. Of that 2098, we're going to multiply by 60 to get our carbs. So we have 1258. And from there, we're going to divide by 4 to get our grams as well. The grams and the calories are important for different reasons, but we want to make sure that we're getting both those numbers. So we're going back to the 2098 for the fat. We're going to multiply that by 40%, and then we're going to get the 839.20. The 839.20 kcals is going to be divided by 9 again, and we're going to get 93.2 grams. If we add those all back together, we get our original recommended intake. And also, if you double check, say you really mess with those ratios, you're trying to really customize something, but you're afraid that maybe your ratios of macronutrients are outside what the recommendations are in the book. The 45 to 65% for carbs of the recommended daily intake for all the calories you eat in a day, or the protein 10 to 35%, or the fat 20 to 30%. Maybe you're worried that you are way off on that. And that's just science. That's just things that are proven that most people will thrive off that bracket of calories, unless you're doing something keto or something a little different. But in general nutrition, those recommendations are going to hold standard. These equations that we do need to also be sometimes checked on the back end to make sure that they're still within those ratios. So if you take the calories that you recommended for each macronutrient and divide it by the total recommended intake, you're going to get the percentage of what is allocated to that macronutrient as far as calories. And if it exceeds or is under that bracket of the window of what it should be, on the previous slide that we discussed, the fat, carbs, and protein, little ratios there, what it should be of total diet, then we need to go back and rework our numbers with different smaller or larger numbers to make sure everything lines up. So if you have any questions, please feel free to reach out. We are available in the Google Classroom. You can call us, email me. We can even do like a Zoom chat or something if you need a little bit of help. We will be back in the classroom on the 27th as well. This isn't, again, a way to take away from your program as far as being in person. It's just kind of a Band-Aid, and with this unfortunate circumstance, we all hope that Roy feels better and everything is good to go. And on the 27th, he will for sure be back in quarantine and safe for all you guys as well. Yeah, just let me know. The last bit here that we're going to be covering today will just be the coaching, and then we will be done with today's lecture, and we'll be catch up next week for some more.